Here's another simple case, okay, where you have one slow step, but it's preceded by very fast reversible steps. Okay, so this particular example, let's look at this reaction of 2NO plus Br2 gives you 2NOBr. Okay, the rate law for this is equal to K times NO squared, okay, times the concentration of bromine. You might say, based on that rate law, it seems like something that would be consistent with that would be one single step where you have two NOs and a Br2 colliding to give you your products, right? One elementary step, two NO molecules involved, a bromine molecules involved, all three molecules collide and they give you a product. That would be consistent with that. But remember what we said? There could be more than one mechanism that would be consistent with an observed rate law. In fact, okay, if you can come up with a mechanism that doesn't involve more than a bimolecular step, if all your steps are either just unimolecular or bimolecular, that might be actually more plausible, as opposed to one where you actually have three colliding right away. So here's a proposed mechanism that might be consistent with that, okay? Like I said, a one-step thermomolecular reaction is certainly consistent with that, but it's not likely. So here's a mechanism that would be consistent with that. So here's your first step. It's fast reversible, so I really should be drawing two arrows there, okay? So in the first step, an NO collides with the Br2, and they get stuck to form NOBr2. And then that's reversible. That means when they get stuck, the NOBr2 could just also split up to give you back NO plus Br2. And then step 2, your NOBr2 collides with another NO and gives you your two NOBrs, which would be your products. Okay, so if you combine these two, what do you see? The overall reaction is, let's see, NO plus Br2 gives you NOBr2, and NOBr2 plus NO gives you 2 NOBr. If you combine these two, what happens? Your NOBr2 cancels out, and your overall reaction has two NOs, right, plus Br2 yields 2 NOBr. Okay? So what's the predicted rate based on this reaction, this mechanism? If this was the mechanism, what would be your rate determining step? Step 1 or step 2? Step 2, the slow step, right? So we say you would expect to observe the rate law to be K2 times concentration of NOBr2 times concentration of NO. All right? Now, that's not what the rate law is. What's our rate law? It's K times rate equals K times NO2 squared, NO squared times Br2. Well, what's the problem with this rate law right here? This NOBr2, we are proposing it as an intermediate. Okay, generally you don't write rate laws in terms of intermediates because intermediates are not something you can easily control in the lab. In fact, they're very hard to measure. But we have, what we did here is we have set up the mechanism so we can express this concentration of the intermediate in terms of things that are easily measured in the lab, like the concentration of reactants and products. So we're assuming that the first step is fast and reversible, right? So if we're assuming that the first step is fast and reversible, then we say, okay, step 1, forward rate, forward reaction, the rate, so we call that V1, is equal to K times NO times Br2. Okay? The rate law for the forward reaction for step 1 is K times NO times Br2. What's the rate for the reverse reaction for step 1? V sub -1, that's usually how we would write it, is equal to some constant K times, what's the reactant for the reverse of step 1? What do we mean by the reverse of step 1? The product is behaving like the reactant and the reactant is behaving like the product, right? So this is your reactant for the reverse of step 1. So it's equal to K times the concentration of NOBr2, okay? And now, the rate constants for forward and reverse reactions are not going to be the same. So to make that distinction, we're going to call this K1 and we're going to call this K sub negative 1. Okay, those are just labels. K1 is the rate constant for step 1 going forward. K sub negative 1, that's the negative 1, that's just a label. That's the rate constant for the reverse of step 1. Okay, so now, we can assume then, we're assuming here that since we're assuming that step 1 is fast and reversible, that means throughout most of the reaction, these two are going at equal rates. In other words, we're going to assume that the forward reaction, okay, V1 is equal to the reverse reaction for step 1. So V1 equals V sub negative 1. Okay, so this is V1 right here, and that's V sub negative 1. Well, if that's the case, what do we get? Let's rewrite that here. We're going to say K1 times NO times Br2 throughout most of the reactions. Got it wrong. Got it written wrong. Okay, here. K1 times NO times Br2. The forward rate for step 1 is equal to the reverse rate. Okay? Is equal to K sub negative 1 times NOBr2. Let's look at this. Well, if I did this, you'll notice that I can solve for NOBr2 in terms of NO and Br2, which are easily measured. Okay? I'm using this equation, I can get an expression for my intermediate, concentration of my intermediate in terms of the concentration of my reactants NO and Br2. How do I solve for the concentration of NOBr2 here? Divide both sides by 1. Divide both sides by K sub negative 1, right? So I can say the concentration of NOBr2 is equal to K1 times NO times Br2 over K sub negative 1. Okay? So I have an expression for NOBr2. I can plug that into my original expression, which was, what was my rate law for my slow step? Let's go back to our slow step, and which is the rate law for my reaction, right? We say that rate is equal to K2, it's right here, times NOBr2 times NO, right? And remember we said we don't like to see this in our rate law because we can't determine that experimentally. But now I have an expression for NOBr2 down here. So this is going to be equal to K2 times, this is the expression for NOBr2. This is going to be times K1 times NO times Br2 over K sub negative 1. And then this one goes down here. That's NO. Okay, so what I've done is I've replaced the concentration of NOBr2 by this expression down here. So how can I simplify this now? I can simplify this to say I'm going to collect all of these constants right here. These are all constants. I can just call them all into a constant times a constant divided by another constant is just another constant. So I'm just going to call it K. And what is NO times NO? NO squared, right? And I have Br2 right here. So here's a rate law that you can predict from this mechanism right here. So this proposed mechanism right here, we say is going to be consistent with the observed rate law, which is second order with respect to NO and first order with respect to BRT. Okay?